Every major AI model you've heard of, ChatGPT, Gemini, Claude, is built on an idea that's more than 10 years old. It works. It scales. And for a long time, everyone assumed that's as far as AI architecture could go. But DeepSeek just dropped a research paper that says, no, there's another way forward. And if this idea holds up, it could completely change how powerful AI models are built from this point on. To understand why this matters, we need to talk about how large language models actually work. Modern AI models are built in layers. Your prompt enters the first layer, gets processed, then passed to the next, again and again, until the final answer comes out. During training, when the model gets something wrong, a signal called a gradient flows backward through all those layers, telling each one how to improve. Years ago, researchers discovered a big problem. When models got too deep, those signals would either vanish or explode. Training would slow down, or completely fail. That's when residual connections were invented, and they saved deep learning. Residual connections created a shortcut. Information could flow forward and backward without getting distorted. Suddenly, very deep networks became stable, reliable, and trainable. That success locked the design in place. The hidden trade-off residual connections weren't wrong. They were necessary. But they came with a trade-off. They forced all information to move through one narrow internal stream. For years, this wasn't a problem. Bigger models, more data, more compute, everything kept improving. But as AI started tackling harder reasoning tasks, that narrow internal pathway quietly became a bottleneck. Not because it was broken, but because it was doing exactly what it was designed to do. Researchers started asking a new question. What if, instead of one internal stream, we pass multiple streams at the same time? More internal communication. More flexibility. More reasoning capacity. This idea became known as hyperconnections. On paper, it looked like a clean upgrade. But in practice, it failed. Early training looked fine. Loss went down. Metrics improved. Entire training runs became useless. At scale, that kind of failure is unacceptable. And that's why hyperconnections never made it into production models. DeepSeek's breakthrough, MHC. This is where DeepSeek stepped in. Their new approach is called Manifold Constrained Hyperconnections, or MHC. The idea is surprisingly simple. Yes, allow multiple internal streams. But never allow the total signal strength to grow or shrink. DeepSeek enforces strict mathematical rules on how those streams mix. Every row sums to 1, every column sums to 1. That means information can be redistributed, but never amplified or dampened. Stability is preserved by math, not by tuning. They achieve this using the Sinkhorn-Knopp algorithm, projecting the mixing process onto a geometric space called the Birkhoff polytope A. The result? Even across dozens of layers, signal strength stays stable. No explosions. No collapse. Real results. Why this matters? This isn't just theory. DeepSeek trained real language models using MHC, 9B27B parameters reasoning heavy tasks. GSM-8K, math reasoning, 46.7 right pointing arrow 53.8 BBH, logical reasoning, 43.8 right pointing arrow 51 mmLU, general knowledge. At this scale, those are huge jumps. Why? Because widening the residual stream gives the model more internal workspace, a completely new axis of scaling. If changing how information flows inside a model delivers bigger gains than just stacking more layers, what else in AI do we think is solved, but actually isn't? Down finger, drop your thoughts in the comments. Thumbs up if this breakdown helped you understand what's really changing in AI, hit like. Bell, subscribe for more deep dives like this. Thanks for watching.